Hello, everyone. My name is Nuno. I'm an engineer at NVIDIA. And I'm here today to talk to you about GPUs, why I find them interesting and why I think you might find them interesting as well. I guess a lot of you have had courses where you do computer graphics, right? If you have computer graphics background, raise your hand. Yeah, good, nice. So I guess you guys all know what a GPU is. Maybe? No? Yes? So a GPU, or graphics processing unit, is any kind of hardware that can take a bunch of data, process it, do some computation on it, and generate an image. So you could think of an old graphics card as a GPU, but for the most part, they were a dumb frame buffer. You just wrote into a piece of memory, and that represented the image, and then all it did was scan that out over the VGA cable. GPUs involve some processing power. So if the chip can't do math, it's generally not considered a GPU. So these days, some people have been comparing GPUs to supercomputers. And GPUs are not really supercomputers, I would say, but they're pretty close in more ways than one. So first and foremost, computing power, they are comparable to supercomputers of about, I would say, maybe 8, 9 years ago, where 9 years ago you'd need about, I don't know, I have some numbers here, 9,000 Intel CPUs on a cluster to get 2 teraflops. And nowadays, you can get that with 2 consumer GPUs, and you pay less than $1,000 for that. So, technology always advances very, very quickly, so that's not really a surprise. But still, it's a very fast pace. The other reason, and perhaps more important, is that GPUs can be seen as a stream processor, and the programming model for that is very close to what the programming model was for a traditional supercomputer. So in other words, you have a huge number of cores that you need to keep busy. And instead of having them all in a room, you have them all on a single chip. That's the main difference. And so this is my talk in one slide, for the benefit of those who might want a faster, shorter version. Why are GPUs interesting? They started by revolutionizing computer graphics. What this means is they took a workload that was not really very adequate for CPUs, and they made them run very fast, very cheaply, which means that computer games and other computer graphics applications could now do much more interesting things. They could draw images with a lot more detail. The same seems to be happening for general purpose computing. So eventually, GPUs made the leap towards more general purpose computing, and for some workloads, they provide very, very big speedups on the order of hundreds of times. And so now for the long version of the talk. Here's what we're going to talk about. First, what is 3D graphics, and why do we design a chip this way? How do we design a chip to do 3D graphics? And then we'll see how people try to trick those chips into doing computational work, even though they were still pretending to do graphics. After that, well, hardware vendors sort of adapted and started to do chips that were more suitable for real computation. So we'll see how we can adapt our initial design to do real computation more efficiently. And then a few very cool applications that people have found for GPUs, and a little bit on how you can also use them yourselves. And finally, since, well, I'm a local, I was told that this would be interesting, that you could relate to this, so I'm going to tell you a bit about how I got a job at NVIDIA. OK, so how do we make a graphics chip? Has anybody ever made a graphics chip? No? Damn it. So what are the goals? What are we trying to do? This image is an image from a demo that NVIDIA made. It's the human head demo. This is actually sort of old, and I'm sorry the quality isn't that good on this screen. It looks better than that. And it runs at about at least 30 frames per second. So in other words, interactive rates on a GPU from about 2007. We don't really do any pre-computation or any fancy tricks. We try to simulate as much as possible what would be required to accurately represent human skin. So this is the goal, I guess. Make great images. If you take a model, you want to show it to people in an appealing, detailed, and convincing way. Or perhaps not even convincing. Perhaps you want to draw a cartoon or something. In any case, you want to make it interesting. And you usually, interactivity is important. So if we can render this offline, right? And we could do this offline years and years ago. But offline rendering isn't really useful for, say, games, of course. It's useful for movies to some extent. I mean, most movies are rendered offline. But for most applications, we do want interactivity, which means that we have a time budget to draw the image. That time budget being 30 milliseconds at the most, usually. So that's about shooting for about 30 frames per second, which is sort of the limit at which games start to become less playable. And it turns out that the best way to do that, the best way to achieve these goals, is to build gigantic hardware to run graphics. Of course, by gigantic, I don't mean a house full of computers, but a big chip dedicated to this. The applications for computer graphics should be pretty familiar to you guys. First and foremost, games. Everybody plays games, and games really do drive the industry forward. In fact, most of this came about because of games, because people want to play games, and it turns out that playing games on a CPU doesn't really work very well, and we'll see why in a minute. I have an image from Avatar here. As I said, movies are usually rendered offline, but increasingly, real-time techniques have been creeping in. For Avatar, while the actors, so Avatar is a movie that was entirely computer-generated, except that the acting was not computer-generated, so it was actual motion capture. And we worked closely with the director and the producers to get technology in place that enabled them to, while the actors were wearing those ridiculous motion capture suits and doing the acting, they could actually see on a monitor a preview, a render of the movie in real time, what it would actually look like. And of course, it wasn't as high quality as this, but it was good enough that it made the production and the shots easier to take. There's also an image of medical visualization here. So we're looking at a skull, I guess, and something like that. I'm unfortunately not a doctor. This is an area where speed is important, but accuracy is even more important. You don't want to, put a bone in the wrong place, or draw something that looks okay but actually isn't, and you're hiding a tumor from a doctor. It doesn't really work very well. It's a very important field, and it has some specific requirements that make it quite interesting, a bit more than it sounds like. So let's go through the process of generating an image from a model. So we start with a 3D model, and this would be a representation of a 3D model. So a 3D model is, as you guys know, points in space that together form triangles with certain properties of like color, texture, and then you have, say, lights inside your scene. And you want to generate a 2D representation of the model that looks convincing, that looks appealing, that looks interesting, like this guy here. So this is a view of that model that I showed. So that's the sled that the guy is standing on. So how do we do this? Well, we start with a model, usually made up of triangles. So we go through each triangle, and the first thing we do is we project it onto a 2D plane that contains the screen. This is done by using a 4x4 matrix transform, usually. We also do some more processing on each vertex to determine certain parameters that apply to the lighting model that we're using. So for instance, you might want to compute the angle that a given light is hitting on the vertex, on the polygon at that point. So you do vector subtraction and a dot product for that. Second step, called rasterization. So screens are made of pixels. They're discrete. We're talking about a discrete 2D space. So we have to discretize the triangle, so to speak. So in other words, we determine which pixels the triangle is covering on the screen to figure out which pixels we need to color and shade. And of course, the next step is take each of those pixels and do some calculations on it to determine what the color of that pixel is going to be. This is heavily dependent on the lighting model that you chose to use. You can also use, say, images you can read image data to use as textures and apply, say, if you're drawing wood, apply a wood image to the polygon to make it look like wood. And finally, you write those out to the frame buffer, and that goes out to display. So this is actually a very, very old concept that has maintained its validity up until now. So most graphics APIs expose this. So start with a model, process all the vertices, rasterize, and process all the pixels, and the result goes out to display. OpenGL, DirectX, they all work like this. And so if you were to implement this on the CPU, which for years and years everybody did, you're looking at 2 loops. So 1 loop for each vertex that you have in the model. Or actually, you might want to loop over each primitive and loop over each vertex inside the primitive. Inside each vertex, you're going to do, in this case, we're talking about a matrix multiplication and the dot product to compute the angle for the light. Right? Then you rasterize this, and you get a list of pixels out of the rasterizer. And for each pixel, you're going to have to do a bunch more calculations to determine the color. In this case, we're going to take a texture, multiply it by the incident angle of the light to modulate the intensity of the color that you apply to each pixel depending on the angle of incidence to the light. And like I said, for years and years, this is all that could be done. These are 2 screenshots of, I guess, fairly high-end CPU renderers. This is, of course, you guys know this. This is Quake 2 and Tomb Raider. A couple of the last few games to even have a CPU rasterizer. And this doesn't look very good, does it? I mean, it looks blocky, and it's kind of choppy if you're trying to play it this way, unless you make the resolution very, very low, in which case it's even blockier. And so people kept for years trying to optimize their renderers so that they could have more time available in each frame to draw more detail. So if you have more time, you can draw more pixels, so you can increase the resolution, or you can add higher resolution textures, more detailed geometry, or what have you. And so, well, people tried. Developers spent many, many hours working on this, and it turns out that this workload just doesn't fit CPUs. We're talking about 96, 97, so there was a single core. Nobody had dual core or dual CPU systems. The big problem is memory access. So in CPU land, usually memory is much slower than the CPU clock rate. So if you're going to do a round trip to memory, that takes a lot of time and a lot of CPU time. So the CPU can stall for many, many cycles when trying to access memory, where otherwise it could be actually doing a lot of computation in that time. There's other problems like the instruction cache is usually too small to fit the entire rendering loop. And this means that every time through the rendering loop, you're going to blow through the instruction cache and generate even more memory traffic, which, as we've already seen, there isn't a lot of bandwidth available for that. And CPUs are very, very good at running code that jumps around. They have a lot of hardware to do branch prediction, which is really good for a lot of workloads because, well, it can start to do prefetching on the instructions that it's going to jump to. But we didn't have a lot of branches in the code. We had 2 loops. Inside the rasterizer, you're going to find a few more branches, but not enough to justify the use of branch predictors. So they're there, but they're sort of wasted transistors. OK, so CPU doesn't work well enough. So the problem now becomes, how do we build a dedicated chip for this without spending too much money? So going back to our pseudocode, if we look at both of those loops, there's no interdependence between each vertex, which means that each vertex can be processed independently. And the same goes for pixel. And the main difference between vertex and pixel is that there's usually a lot more work to be done in pixel processing, simply because, well, you can generate many, many pixels with a single triangle. So three vertices can cover the entire screen. And that's a lot of pixels. So the obvious way to optimize this is to parallelize vertex and pixel processing. Since they're all independent, they can be processed in any order. We can try to parallelize this by adding many units to do this sort of processing. And of course, we want to avoid memory bottlenecks, which means we need very, very fast dedicated memory for our chip. There's also issues with locality of access, which means when you're fetching data, usually on the CPU, caches work in a linear fashion. So you have one address, the cache will fetch the four subsequent addresses, for instance. This works for some of the memory traffic that we generate. But if you consider, say, a texture, and we're fetching from a texture to color a triangle, the memory access pattern for that is horrible in terms of cache because, well, it's not going to fetch linearly. It's going to fetch like a diagonal. And if you consider that the memory layout is going to be pitch, which means one scan line after another, you're going to read one address here, then another one over there, then another one back there, and the cache just doesn't work very well for that. So we need some sort of caching mechanism that works well when the locality of access is a small 2D tile of a big image. So very quickly, for vertex processing, we have, as inputs, we have constant input parameters like the transform matrix or light positions or whatever else you need that's fixed per primitive. And we have per vertex parameters like, of course, position, maybe color, normals, and what have you. And the output is a transformed vertex position, which is basically a projected vertex on the screen. We also compute any vertex parameters required for the lighting model, in our case, the angle to the light, maybe the distance if we want to do attenuation. So we have our inputs here. The obvious way to solve this problem is you create a small unit that goes and fetches from memory and generates work for 3 vertex processors, which are down there. And why 3? Well, we have 3 vertices in a triangle, so sounds like a good choice. These vertex processors are actually quite simple. So we're dealing with floating point math, but we don't actually have to implement floating point math here. I mean, at this point, back in 96, 97, precision requirements were quite low, and you could do fixed point instead of floating point. So maybe 16-bit fixed point at most is good enough. And you really need, well, you really need a multiplier and an adder for each of these units. You don't need much more than that. You can get by with very little hardware on each of these units, which means you can make them small, which means you can make them cheap. Rasterization isn't a very interesting step. It's mostly serial by nature. Well, you can rasterize in tiles, but that's still somewhat serial in nature. The input is just the transform vertex parameters from the previous stage, and then the output is a list of pixels that are going to be shaded. The rasterizer is usually also responsible for interpolating any per vertex parameters along the inside of the primitive. So here we go. We add a little rasterizer that dumps pixels into a small FIFO. And finally, for pixel processing, I mean, this is really the same concept as vertex processing. So do everything in parallel as much as you can. The inputs are pixel positions, any interpolated parameters, texture images we might be using, and the output is a color. And so we add another dispatch unit to schedule work across an array of pixel processors, and we had a whole bunch of pixel processors, really as many as we can fit within our budget. Precision requirements for this are even less than Vertex, so this is even cheaper per unit. You can make do with, I don't know, maybe 10 or 12-bit fixed point math, although you do want to preserve 16-bit precision for color. But internal math can be done in lower precision. And finally, you have a big fat memory bus and a texture unit to read textures from memory into the pixel processors. As a curiosity, this is a very, very early GPU, or you'd probably not call this a GPU because it's multiple system boards inside a big computer. This is SGI's reality engine from '93. So you can see that the architecture is fairly similar. What they call fragment generators are actually rasterizers. So SGI had this strange naming for pixels. They call them fragments until they actually hit memory. And so you can see the architecture is pretty similar to what we have. Now, consumer GPUs started out by being half a GPU, not really a full GPU. In other words, they only did the rasterization and pixel processing. This was due to cost, mostly. I mean, it's easier to make a small chip to do just this. And so this is a screenshot from Quake. I guess you guys all know this. This is running on the CPU. This is what a 1996 game high-end CPU renderer typically looked like. So it's blocky and very, very brown, and didn't really look very good. So you add half a GPU, and I'm sorry, but you can't see anything. Id games are famous for rendering many shades of black. Thank you. So you have half a GPU, and you get a lot more resolution. You get a lot more detail. And you can see this is still the same game content. This is still the same models, the same assets. They're just being rendered with more pixels for the most part. So going from here, GPUs evolved in a very different way compared to CPUs. Where CPUs tend to go in a, well, clock rate tends to go up. With GPUs, that's not really the case. So GPUs scale by becoming wider, which means more units inside each chip. As an example, NVIDIA's TNT2 card had a 150 megahertz clock, but the following card, which actually had higher performance, had a lower clock rate. This is really because for this kind of workload, it is more important to have very efficient access to memory than it is to have very high clock rates in the core processing units. And this is in stark contrast to CPUs, where memory clock rates for CPUs tend to be very, very low compared to the internal clock rate for the CPU itself. Once games got rid of CPU-based renderers, all of a sudden, this is in the space of about 3 years since the last screenshot, all of a sudden games became much, much more detailed. So developers were sort of shackled initially to the CPU-based renderers that they still had to support. So you either had assets that worked well on the CPU renderer and then didn't really look very good on the GPU version, or you had assets that worked really well for the GPU, but then the CPU would struggle to keep up. Eventually, developers just said, well, I want a GPU for my game, so you have to buy a GPU if you want to run my game. And all of a sudden, image quality went up dramatically. So traditional CPUs are really, really not suited for graphics work. There's a number of issues that would need to be solved and were really solved on time. And GPUs came into the market and then just swept it away. I mean, CPU renders just disappeared overnight. In the space of 3 years, we went from blocky software-rendered games to much more detailed GPU-only games. And so at this point, we have a lot of computing power inside our chips. And people started to try to do some creative tricks to harness that computing power. In the meantime, well, the graphics guys were already complaining again. So, had just given them GPUs that made their games run fast and made them a lot prettier. And a couple months later, they were already complaining that they were too slow and too limited. The first important change that happened was that GPUs became programmable. So rather than implement a fixed lighting model, a fixed shading model, we can now download code into the GPU. So here's our old model. And what we change is, instead of having a fixed set of parameters as inputs, we just say, OK, this can fetch from memory, and it can read whatever you want. And then you're going to download a little program into the vertex processors and the pixel processors that's going to do whatever you want with the data that we just fetched for you. So this allows applications to really, really control the rendering pipeline. We don't have to spend transistors or time computing values that are superfluous because they end up being disabled, and so they're discarded. And of course, this brings a lot more flexibility to game developers and allows them to do a lot more interesting stuff. In terms of our old pipeline, what this changes in our pipeline is that the green arrows are now steps that are programmable. So developers decide exactly how their triangles are transformed and what computation goes in there. And they also decide exactly how their pixels are shaded and what kind of calculations are done there. And this allowed games to become much more interesting. So this is a screenshot from Half-Life 2, which is about 2004, I believe. And if you look at, well, there's a number of effects that wouldn't be possible with a traditional fixed function GPU. If you look at the water, for instance, the way this could be rendered is you render a plane, and at each point, you're going to fetch a pixel from a texture that contains a reflected image that we see on the surface of the water. And you perturb that pixel, the position of the pixel that you fetch, using some noise function that'll generate the ripples and the waves that we see and the reflection. This is something that would just not be possible using traditional GPUs. This is a screenshot of Doom 3, and about one of the very few screenshots where you can actually see anything other than black. And I wanted to have a screenshot from Doom 3 because it was a very important game in terms of GPU shading. It sort of pioneered the idea of per pixel lighting, although others have been playing with it as well. This screenshot doesn't have a lot of per pixel lighting effects visible. But the only screenshots I could find where I could really see that were, I thought, a bit too gory to add to this presentation. So there, this is another typical game of this era. This is also a 2004 game. Developers also decided to do funky stuff using shaders, like cartoon shading, for instance, where you draw a teapot or a gun that looks like a cartoon. This is mostly a curiosity. In the meantime, the non-graphics people were looking at this and thinking, well, there's a lot of processing power here. I mean, there's a bunch of units that are computing pixel value or color values from pixels. It sounds like they can do a lot of computation very, very fast. So is there maybe a way that we can harness this to do some other form of computation that's not generating an image? So the first thing that they tried to do, just bypass vertex processing entirely. So you can control what you do with the vertex processor. So you can make it do absolutely nothing. And this way, you have a primitive, it gets sent to the rasterizer directly, so you know exactly which pixels are going to be generated. And this allows you to focus on the pixel processors themselves. And so this is what we've been doing, right? So we have an image used as a texture that we read for each pixel. And we compute the color of each pixel as the texture fetch modulated by the light angle, which kind of gives you a shading effect that sort of mimics the way light reflects off of a diffuse surface. Of course, we can do something else. We can say take two images and add them together. And this, I mean, this is still graphics. This is something that, say, Photoshop would do. There's a blend mode in Photoshop that does exactly this. However, if you do the exact same thing, but you look at the data slightly differently, you can download floating point values into these textures. And so that means you could download, say, a matrix. And if you run the exact same program with the exact same parameters, but you put matrix data instead of image data in those textures, you end up causing the GPU to compute the sum of those matrices. So this is not graphics. This is linear algebra. And so this is what people started to do. There was a lot of processing power available on the GPU, and people wanted to use it, so they became creative. So you take the vertex processing out of the equation, just download your data as texture images, and then pretend that you're drawing an image, and the GPU will happily draw that image for you. The fact that it's not an image is inconsequential because the GPU doesn't care. And why did people do this? Well, GPUs are very, very good at graphics, right? That's what they're designed for. If you can make your workload look like graphics, then the GPU will be very good at processing it. So you get massive speedups if you're doing something that can map to this model well enough. And it turns out that there's a lot of problems that can actually be mapped to this model. So adding two matrices is very, very obvious. You can also do matrix multiplication, which is a bit less obvious, but still maps pretty well. Of course, you can do image processing, and computer vision algorithms also evolved working on top of graphics APIs and trying to hack away the graphics part of it. So at this point, people were asking for GPU compute. People were very interested in harnessing this power more efficiently. And hardware vendors, of course, started to look at this more seriously. So if we look at the GPU as a computer, rather than just a graphics chip, the computational model that we see is that we have many, many threads running inside the chip, where each pixel corresponds to a thread. They're all running the same code, right? So they're all running the same pixel shader, so to speak. But each pixel is processing a different data point from your data. So you can think of the GPU as an N-core CPU, or a stream processor, if you will. How does this differ from graphics? It really doesn't differ that much, except that vertex processing is generally not useful for compute loads. So since people were very, very often bypassing the vertex processors, hardware vendors started to look at this and try to figure out, well, how can we make this more efficient in order to expose compute for our GPUs? So we have our model GPU, and I simplified it a bit in this slide. So we have specialized units for vertex and pixel, but we've seen that they sort of do mostly the same thing. And since they're now programmable, it doesn't really make a lot of sense to have separate units anymore, because you can just run different code on the same unit and do vertex and pixel processing on the same unit. So this is what happened. Instead of having specialized units, it became more generic. And we have a dispatch unit that can dispatch both kinds of work, both vertex and pixel, to different units. So in this case, we have a primitive coming in, and we have a bunch of vertex processors working on it. The output goes to the rasterizer, as usually. And then once the output from the rasterizer gets fed back into the dispatch unit, it starts scheduling pixel work on the same units, in this case, the units that were idle. Of course, you also need the rest of the hardware. You need very fast memory. You need texture units to fetch from memory. And it turns out that the graphics guys actually loved this idea. And this is because they no longer had to try to balance the work that they threw at vertex versus pixel. So we have a bunch of pixel units who have usually a lot less vertex units. If your game has a lot of geometry and each triangle is small, you're going to have a problem because your vertex becomes a bottleneck. With this, the chip itself can actually load balance between vertex and pixel. And of course, if you want to do compute on the same chip, you just turn off all the units that you don't need for compute. So you bypass the rasterizer. You may bypass the texture units, although they can actually be useful for compute. And you get a compute-capable chip. of course, you also need, I guess you also need to do a few more changes. Compute has higher precision requirements. So we were just talking about chips that, you could get by with 16-bit floating point or fixed point even for graphics. Compute really needs a full precision floating point. I mean, at least 32-bit, but people do want 64-bit floating point. Also, in general, if you're dealing with geometry and pixel data, each of your work units, each of your data units rather, is not just one value but four. So you have vertex position, that's x, y, z plus the homogeneous coordinate. If you have colors, that's RGB plus alpha. For compute, vectors are not as interesting, so you probably want to make them scalar as well. And the graphics guys also like this idea, because graphics workloads, once you make the chip programmable, don't really need to necessarily work on vectors. You can do a lot of scalar math that's useful before you actually go into, say, multiplying a color by some scalar value. And this is mostly a curiosity. This is what a real GPU architecture looks like. So at this point, we have a full compute-capable chip. This is the GTX 200. And as you can see, the rasterizer, the vertex shader, the geometry shader, which wasn't there before, the pixel shader, are now part of a thread scheduler. So it's basically, we have one unit that feeds work into a huge array of little units that actually do the work. So those little green blocks in the middle of the image inside those big blocks are vertex and shade and pixel and compute processors. And down below, we have our memory bus with texture units in between. We also have raster output units, which deal with writing data into memory for the frame buffer. And we have some atomics, which are useful for compute. But I'll go there now. So what can you do with a GPU? Well, you have all this processing power. You expose it using some API that's convenient. What do people do with it? OK, I'll admit that this is pretty grim. So CT scans actually cause cancer. And there's an estimated 28,000 patients that get cancer from CT scans alone each year. It turns out that, so a CT scan is basically like a series of pictures, except that they use X-rays rather than visible light. And just like in a camera, you can increase the sensitivity to take the same picture with less light. But in doing so, you're going to increase the noise. In this case, you can reduce the radiation and increase the sensitivity and still get the same image, but with a lot more noise. So you have to do some sort of image reconstruction to get useful data out of this. Research done at the University of California in San Diego found that using advanced reconstruction algorithms, you can get the same output from 35 to 70 times less radiation. So there's a lot more noise, but you have a lot more processing to go with it. So you get mostly the same image. Unfortunately, if you run this on the CPU, it's going to take about 2 hours to process an image. So you have your patient inside the CT scan, and the doctors are waiting for the image to come through to figure out if they need to take another one. It doesn't work very well. I mean, standing in there for 2 hours is probably going to kill the patient anyway. You can do this on the GPU, though. And it turns out that if you do this on the GPU, it takes about 2 minutes. So 2 minutes is useful. 2 minutes for this is doable. And so people are starting to use GPUs for image processing from CT scans to try to reduce the amount of radiation that they spray on patients. Now, this one is really, really, really interesting. Most heart surgeons do not operate on a beating heart for obvious reasons. I mean, it's beating, so how do you suture a heart that's moving and beating? There's actually about 2% of surgeons willing to do this, but not every time. And there we go. Usually, the heart is stopped for heart surgery. However, there are new techniques emerging that allow you to do surgery on a beating heart by using image processing to essentially create a view of the heart that is still. And the way this works is you take two cameras, a stereo endoscope, you put it next to the heart, it captures images from the heart. Since this is a stereo system, you can apply traditional computer vision algorithms to try to reconstruct the 3D model of the heart at each frame. And if you do this fast enough, you can actually reconstruct the beating of the heart in a 3D model. And once you have this 3D model, you can use it to do two things. First of all, you can reproject the output from the camera to look like the heart is not beating. And second of all, you can use the 3D model to guide a robotic arm, which can operate on the beating heart, while the surgeon operates that arm remotely through some set of handles or some interface that doesn't require the surgeon to accompany the motion of the heart. And if this works, I actually have a video of this in action. Let's see if I can show it. Here we go. No, sorry. So this is what it looks like. So we have the image from one of the stereo cameras in the middle, and this is what the surgeon would see. So in other words, the image below is stabilized and compensated for the beating, the heartbeat. And this is a representation of the 3D shape that's reconstructed from this stereo image, or stereo video stream, rather. And this is what will be used to guide the robotic arm that the surgeon operates. And of course, you can run all these algorithms on a CPU, but on a CPU, you can't do this in real time. So it's not really useful. You can't post-process a heartbeat to then figure out where to stick the needle. That doesn't work. GPUs allow this to run in real time, and there's a lot of research being done on this topic to try to make this usable for surgeons. And of course, there's numerous other applications from, say, a video decoder and encoder, where you see a 400-something speed up by just using a GPU instead of the CPU. A number of computer vision algorithms are very well suited for the GPU and get very, very big speed ups as well. There's things like smoke simulations for graphics, and in fact, compute and graphics mix very well together since, well, they run on the same chip for one, and you can use the results from compute to guide your graphics renderer. So you can do, say, smoke simulations using compute, and then render the output of that smoke simulation using the normal graphics units. What else we have? Oh, we have sequence alignment. GPUs are increasingly being used to sequence DNA. DNA sequencing involves processing a lot of data, and it turns out that the CPUs become a bottleneck very, very quickly because DNA sequencing kind of scales in the same way as a GPU. It becomes wider because you can do more and more strands at the same time. And at some point, the CPU just can't keep up, but the GPU generally can. So we're going to do a quick overview of how to use a GPU to solve computational problems. So we've seen that GPUs process data in parallel. It's like you have hundreds of processors running on your data. Each processor will take a single data point and transform it into another data point. They all run the same code, so it's effectively like a stream processor. How do you expose this for developers? Well, NVIDIA has one option, which is CUDA. It's a C-like language that runs on the GPU. So in other words, you write your C code, and you add a few keywords here and there, a few very small extensions to the language that tell the compiler to generate GPU code or to call GPU code from CPU code. It's really as simple as that. There's also an API to manage GPU memory explicitly if you need to. And how does something like this work? What does CUDA code look like, and what does GPU code need to work like in general? So if you're trying to add two vectors of floating point numbers, they're essentially two big lists, and you're going to add them together and get another big list. On the CPU, you're just going to run through all the elements and add them together one by one. That's fairly simple. The GPU has many, many, many threads. So you could do the same thing, except that you're only going to use one of the 512 cores you have. So 99% of the hardware is going to be idle. Doesn't work very well. So you want to think in a different way. You want to think about how to fill up the entire machine such that all of the GPU is doing useful work at any given time. The way to do this, of course, is to launch many, many, many threads and have each thread process just a little bit of data. In this case, each thread will process an element, and you launch a bunch of threads at once, and all the elements get processed at once. This is what CUDA looks like. So it's C code, except that you add a few tokens to it. So there's a global token over there. Basically means this code is going to run on the GPU, but I'm going to call it from the CPU. So the compiler generates all the necessary code behind the scenes to accomplish that. CUDA tells each thread which index it's processing. This is kind of like, say, MPI, if anybody used that before. So in MPI, each node has a rank, and each node is usually a separate computer, though not necessarily. In CUDA, each thread has an index. And if you map thread indexes to elements, you can have each thread process a single element, and each thread will know what that element is based on the thread index. So take the thread index, use that to index into the array, process, do the sum, and write the result in the right place. And then to make this run, there's some special syntax that CUDA exposes. So you just call the function as almost as normal, except that you say this function is going to run on n threads on the GPU, using that strange syntax over there. Another interesting problem that sort of highlights that GPUs require a different paradigm, different way of thinking is how do you sum a list of numbers on the GPU? In this case, you have n inputs and one output. So how do you do this? On the CPU, it's easy. You just go through all of them and add them to a register variable, and that's your result. On the GPU, however, well, you could also do the same thing, but again, you're going to have one core working and 511 cores idle, which is not ideal. Or you can compute the sum in steps, where instead of adding all the elements together at once, you're going to take two elements and add them together into one. And this way, you split the work across threads, sort of like this. So if you have 8 elements, you launch 4 threads, and each thread will read 2 elements and add them together and write out the result. Of course, you have to do this in multiple steps. So you do as many steps as you need to get to the final result of one sum of all the elements that you have. Okay, so let's do a few predictions for the future. And NVIDIA has shipped many, many CUDA-enabled GPUs, about 300 million or something like that, which is a prediction from, or a number from a few months ago. There's a lot of GPUs out there that can be used for computation. And they're pretty much everywhere. I mean, every desktop computer these days has a compute-capable GPU, be it from NVIDIA or any other vendor. And they're pretty much everywhere. Desktops, laptops, cell phones these days have powerful GPUs in them. Some can already do compute. Most of them will be able to do compute soon. Game consoles, of course, have had GPUs forever. I think none of the current game consoles can do compute, but I'm sure the next generation will include compute capabilities for the GPU. Of course, tablets go hand in hand with cell phones. Cars are starting to have onboard computers that contain GPUs that, again, are either capable or will be capable very soon of doing compute. And things like set-top boxes and other applications for GPUs, they're pretty much everywhere. And so this means there's a lot of parallel processors waiting to be used out there. In particular, for mobile phones, this is a graph of shipments for mobile phones versus desktop computers. As you can see, I mean, everybody buys a phone, and a lot of those phones have GPUs in them. Not everybody buys a desktop computer these days. Most people do buy laptops, but not as many as cell phones. I mean, so everybody has an iPhone or a smartphone these days. And all of those require a GPU. And iOS, of course, Apple has their platform locked down, and so they control everything that goes in there, and they require a GPU. And their GPUs can actually do compute. They expose OpenCL, which is another API to do compute. Android also requires a GPU. You can't possibly ship an Android phone without a GPU. Most Android phones do not have compute yet, but they will soon. And also, it's interesting to note that CPU clock speeds have kind of stagnated. They don't get any faster. What they do get is they multiply themselves. So now on a single chip, instead of one core like we used to have, we have a bunch of cores. We have 2, 4 cores. If you throw in hyperthreading, you can consider them to be 8 cores on a chip. So CPUs are also evolving by getting wider, much like GPUs. However, the GPU architecture is much more suited to getting wider, because each unit that you add is a lot less hardware than adding a full CPU core. So it's much, much easier to scale sideways on a GPU. But regardless, I mean, even if you're targeting a CPU, we're not in 1995 anymore. CPUs are multi-core, even if they have 2, 4, 8 cores rather than 500 cores. You still have to write your code to run in parallel. And so long as you're doing that, of course, the programming model is different, but the algorithms that you're going to choose are actually much more similar than if you were simply targeting a single CPU. They're a lot more similar to what you need to run on the GPU. So one way or another, everybody's going to be doing parallel code from now on. And so the line between CPUs and GPUs starts to blur even more. It's not really very hard to port a program to the GPU these days. Okay, so before we go on, does anybody have any questions that you'd like to ask? Okay, please.
I would like to have an NVIDIA board on my Apple computer. Is that going to happen this spring?
I'm probably not allowed to comment on that. I'm sorry. Anybody else want hardware predictions or something like that? Anybody else want to know company secrets? Yeah. Perdão? So the question is there an internship program at NVIDIA? The answer is yes, there is, and it's quite interesting. I'll talk about that in the next few slides.
Okay. I have a couple of questions.
Mm-hmm.
First of all, in one of your slides, you refer to the locality of access across 2D surfaces. What do you mean exactly with that? Are you talking about locality in terms of topology?
So I'm talking about, so the question is, and let me see if I can summarize this correctly. What does locality of access on a 2D surface mean? Is that correct? Okay, so when you're talking about a CPU cache, locality of access means you're reading addresses that are close together.
Oh, you mean like
right? Yeah, right. So if you're reading addresses that are close together, if you're reading addresses sequentially, the CPU cache is very good at optimizing that and reducing memory or hiding memory latency that way. Now, the problem is if you're doing texturing, if you're fetching from an image to use as a texture, the access pattern is going to be very, very bad for a cache that is trying to hide latency for sequential access. Because you could be running on a diagonal if you think of the image space. You could be running on a diagonal, and each point is going to be on a different scan line, which means that it's each point, if you recall that scan lines are usually written one after the other in linear addresses. Yeah. So it's going to be pretty damn awful for caches. What that slide referred to was we want to optimize memory access patterns like this. We want to make the cache run efficiently when you're fetching from a diagonal in an image, right?
My next question is about, do these new NVIDIA GPUs support automatic load balancing, or do we have to implement it?
So the question is, do new NVIDIA GPUs support automatic load balancing? I guess you're talking about vertex versus pixel versus compute?
No, I'm just talking about pure computation.
Okay. I think that's not an easy question to answer.
Because if we go to parallel CPUs, for example, if we have a multi-core machine, we use OpenMP. OpenMP does the load balancing for us. So is there anything like OpenMP?
So, okay, so with CUDA, and I think the same is true for OpenCL, but with CUDA, if you tell the API, I need to run 1,000 threads, the API will not launch 1,000 threads because they will likely not fit on the GPU. But it will launch, say, 500 threads at a time, right? And it will keep the machine as full as possible. So if you're looking to keep the GPU busy, the API will hide the fact that the GPU cannot run 1,000 threads. It can only run 500 or 200. And it will keep the machine as busy as possible. I guess that's the kind of load balancing you're looking for?
Yes.
Okay.
Then you referred to SGI's reality engine. Now, when the Nintendo 64 was being developed, it used the CSGI chip it was called back then Project Reality. Does the reality engine have anything to do with Project Reality? I was just curious.
I doubt it. I don't know, but the reality engine was not a chip. There were multiple boards involved. I mean, each of those, I'll probably go back to that.
Okay, my final question is...
Okay.
Sorry, it's not my final, there's two more.
All right, we'll be here.
Is it possible to, partition the execution of a GPU? For example, can I use a GPU to do pure data computation and use it at the same time to do computer graphics? This would be interesting because if it wouldn't be possible, we would have communication overhead, and that wouldn't be very nice.
So the question is whether you can use the same GPU for compute and graphics.
Yes, computing data, computing pure computation and graphics.
Yes, you can. And in fact, there are interoperability APIs between graphics and CUDA, and also graphics and OpenGL. Graphics and OpenCL, which allow you to do just this. So you take, say, an OpenGL buffer, you run computation on it using CUDA, and then you draw from it using OpenGL again, all without leaving the GPU and all without any stalls of some sort.
My final question, how does CUDA or any GPU treat recursive functions? Can we use recursive functions on the GPU?
I think these days you can. I'm not entirely sure. That was a problem before. Generally, however, you don't really want to do that. So when you're running on a GPU, you have a few instruction schedulers that schedule what we call warps of CUDA cores. What this means is if those warps are executing the same code, then scheduling is efficient. If those warps diverge, then a few of the cores are executing one side of the branch, a few of the cores are executing another side of the branch. We still only have one instruction scheduler for all these 8 cores, so they will have to wait, right? So you schedule instructions for one set of cores, and then you schedule instructions for the other set of cores, and they have to wait for that scheduling. So usually,
It's bad.
Sorry?
It's generally bad.
It is, and recursive functions tend to be pretty bad in that respect. Anyone else?
Quando vamos ver no mercado APUs da NVIDIA?
Sorry?
Quando vê a NVIDIA vai substituir os processadores da Intel?
So I guess the question is, when will NVIDIA make is CPU and GPU on the same chip?
Yes, yes.
Well, let's see. We do have some projects going on to mix GPUs and ARM cores, right? We have this project called Project Denver, I believe, which is basically a Tegra 3 board with a GTX 260, if I'm not mistaken. As far as fusing those two together, well, I don't really know when it's going to happen, or if it's going to happen. It's possible, and it might not be too far off, but it is unknown.
Hi. Let me know if I got this straight. When you want to perform general purpose computing, you have to move the data from main memory to the video memory, and then back again if you want to post-process it, right? Mm-hmm. So if I am doing some interactive application, can this be a performance killer, the moving the data back and forth?
Yes, that can very much be a problem. So usually when you're developing applications for the GPU, since there's two memory spaces, you want to avoid moving from one to the other as much as possible because the PCIe bus is very, very slow. So generally the approach that is taken is, well, you do as much as possible on the GPU, potentially all of your computation on the GPU, even if the GPU is not as suited for some parts of it. It might still be faster than transferring the data back, doing the computation on the CPU, and then potentially moving it back to the GPU. So the trick is really to avoid data transfers as much as possible.
Okay. During the presentation, you talked about atomic operations on the GPU. Mm-hmm. I know they are quite disturbing on multi-cores. They kind of stop everything so that the atomic compare and swap can process. Can you comment on that on the GPUs?
Right. So atomics are expensive everywhere. On the GPU, you have a multi-layered memory architecture where you have different kinds of memory that you can access. So each core has local memory that uses register memory. The GPU is divided into blocks of cores. So each block contains a number of cores, and inside each block, there's a piece of shared memory for the cores inside that block. So no other cores from other blocks can access that memory. And of course, all cores can access main video memory. Now, when you're doing atomics, you're inherently serializing a number of cores. And the less cores you serialize, the better. So you can do atomics on local shared memory, on block shared memory. That's less expensive than doing atomics on main memory. Simply because if you're doing atomics on main memory, you're going to have a lot of cores hitting the same, trying to do the atomic operation on the same address, on the same piece of data. And of course, that creates a lot of contention, especially considering that you can have 512 threads running at the same time. That's usually a very bad idea. Usually, it's much better to do atomics on local shared memory and then maybe move all the data from local shared memory into main memory at once you're done computing it, using another atomic operation, but at least you only do it once.
Okay, just a follow-up question. Does the API expose to the developer that architecture of blocks and layered memory?
Yes, so CUDA does expose blocks and blocks of threads to the application. It also exposes the multi-layered memory architecture that we have. So each block gets a piece of, has its piece of shared memory. You can make each thread take up a chunk of that and do processing on that and pass it on to another thread within the same block. And of course, you can also write to main memory and use, it's a different memory space. So yes, the API does expose that.
Okay, thanks.
Just one question about MPI, which you mentioned. I assume from your comments and from what I know that you can use message passing interface with CUDA, right? So how trivial or non-trivial is that to be implemented, to mix code that obviously has a parallel approach with nodes spread across whatever infrastructure you have with CUDA running on it?
So we do support message passing interface on top of CUDA. And we support some of the networking technologies that are used with that. I think InfiniBand is one of them. I believe, but I haven't looked at the MPI library that we publish very closely. I believe the way it works is really, it's a cluster of GPU nodes as far as MPI is concerned. Given what I know about the people working on that, I would say it's probably very easy to use, but I don't know the answer for sure because I haven't looked at it enough. Any more questions? Anybody?
But it's possible to use it, yeah?
Sorry?
It's possible to use it with...
Yes.
Okay.
O que podemos esperar no futuro das placas gráficas que o poder de computação delas, em termos o que eles podem fazer para os jogos, coisas do gênero?
So the question is, what is going to happen to graphics chips in the future? How are they going to evolve?
Yes.
Well, lately computer graphics has sort of stagnated in terms of games. It has to do a little bit with the fact that the current console generation is lasting a lot longer than manufacturers originally intended, which means that the content that gets developed today has to run on consoles that have graphics chip from 5 or 6 years ago. It's not really cost effective to create essentially 2 different versions of the game, one for consoles and one for PCs, just to get more graphics detail on the PC. Games do evolve, and new games do look better than older ones. But right now, it's somewhat stagnated. So the evolution that's happening in terms of GPU hardware is not just about performance. Nowadays, there's very strong concerns about performance per watt. So in other words, doing the same amount of work with less power, so being more power efficient. This, of course, applies very much to cell phones, of course, because the more power efficient, the longer your battery will last. It also applies to desktop boards. And it's true not only for graphics, it's also true for compute. So if you have a big cluster running a lot of GPUs, you have problems with heat dissipation and giving them all enough power to run. The less power that they require, the less heat that they produce, and the smaller the electric bill at the end of the month. So for a big data center, that's a very important issue.
Como é que se arranja o trabalho para a NVIDIA?
Sorry?
Como é que se arranja o conjunto de trabalho para a NVIDIA?
Okay, so I guess we're going to move on. So what is my background? I got my degree in Coimbra, not too far from here. Did all the usual stuff. I mean, was just another student there. I did take an interest in computer graphics, and my graduation project, I went to Vienna to study physically based rendering techniques, which is something that I find very, very interesting, but it turns out that nobody cares too much about it because it's not very useful. The reason is, and you'd think that, so physically based rendering means you take a representation of the physical properties of the material that you're trying to render, you create a model with it, and then you try to generate an image that's physically accurate, right? So there's some meaning to the data that you're creating. Generally, this means not working in RGB space, but rather with spectral samples of light. And you can get very, very interesting images. I mean, for my graduation project, I was validating images by taking pictures of the same model, same physical model. So we had a little crystal from Swarovski. We had a light box. We had models of that for our physically based renderer. And one way I validated the output of that renderer was by taking pictures of the model and comparing them. So it is that accurate, and it can generate very, very realistic images. The problem is, for the most part, computer graphics are not really about generating realistic images, they're about generating pleasing images. And sometimes the world is just very boring. I mean, if you're playing a game, you don't want it to be physically accurate. You want it to be good. You want it to look good. Not, say, have a player that looks realistic and dull, right? For movies, it's the same problem applies. I mean, the director wants some part of the scene to be brighter. It has to be brighter. It's not going to be, it doesn't matter if it's physically accurate, so that's what the director wants. So it turns out really the only applications for this are architecture and to show architects whether their buildings will look good under just certain lighting conditions and so on. And sometimes rendering products for marketing. But those are quite limited and can also be handled by more traditional techniques, I guess, which might be why this didn't really take off. Anyway. After that, which I guess I just spent way too much time on, so I finished my degree and I went to Deutsche Telekom to do GPU-based computer vision. So I worked on this project it was sort of an interactive installation where there was a screen, there was an image being projected on the screen, and people would go up to the screen and touch it. So it was something like this, right? So you can touch this and it deforms. So if the idea was people would go up to the screen and touch it and deform it, and there was a high-speed camera, a single high-speed camera capturing the shape of a projected image, which would be something like, say, flames, fire, a particle system that follows a finger, something like that. And using that image from the camera and the image from the projector, which we know because we're generating it, the idea was to reconstruct a 3D model of the screen and have that provide some interactivity with the image that we were projecting. So if we detect a finger, we can make the particle system draw something around the finger or something like that. For this, we had a high-speed camera, and it generated, I think it could go up to 200 frames per second. And we couldn't possibly process that on the CPU. So this was back when GPUs were pure graphics chips, and we had to deal with the graphics API. So I spent some time doing that. It was quite interesting work, but eventually I moved on. So after that, I actually got to NVIDIA. And we'll get to how I got there in the next slide. What I've been doing at NVIDIA, I started doing desktop OpenGL drivers by fixing bugs and creating fresh new ones to fix. Also did a bunch of performance optimizations on some potentially famous titles and other applications that nobody has ever heard about. And eventually I became the interop guy. I was in charge of interoperability between OpenGL and CUDA and OpenGL and DirectX. There's not much to say, I guess. It's just moving buffers around from one application to another and allowing to do compute on an OpenGL surface or pass an OpenGL surface to DirectX. And then I moved to mobile. And as soon as I moved to mobile, I was sort of a point of contact for Google on Zoom. I was the NVIDIA driver guy for them. I wasn't the only one. There was actually a team of 2, me and my boss. So I guess it was a team of 1 plus a manager. But anyway, I was the NVIDIA driver guy for Google on that project. I would do whatever they needed. I mean, I'm mostly a graphics guy, but at some points I was debugging HDMI signals and things like that. So it was quite interesting and also quite tense sometimes. And once that project died down, I mean, Zoom is done, I became the Android OS guy at NVIDIA because I had lots of experience with lots of parts of Android. And so I'm currently in the OpenGL ES core team, which develops the OpenGL driver. And I'm sort of the Android OS guy to some extent. So how did I get there? Well, this is what I did. I went to the SIGGRAPH website, clicked on that. Well, actually, the submission is over. They have a program for student volunteers. What this means is they invite a bunch of students, or students sign up for it, and they choose a bunch of students to go and help with the conference. And I don't know, how many of you have heard of SIGGRAPH? Oh, good. A few. So SIGGRAPH is a very, very big conference. It's mostly about computer graphics, but these days not really just computer graphics. I mean, if you have computer graphics, you have, say, movies, right? Movie studios are rendering movies on huge clusters of computers. So you have huge clusters, you have people selling solutions for clustering. So that's really not just graphics. And then the networking people come along to make all of those data transfers inside the cluster very efficient. There's also, of course, a lot of art. Many artists go to SIGGRAPH just to present their art, not really present any research. And if you're into graphics, I mean, this is possibly the best conference to attend. And they have a very good program for student volunteers where they take a bunch of students and make them do random tasks around the conference. I mean, it could be something like waiting at the door, like they're doing. It could be something like checking badges at the entrance. It could be something like folding T-shirts. Or it could be something like escorting speakers around. And depending on what you do, you actually get to know a lot of people. And it doesn't really depend on what you do, rather, because companies are usually very, very interested in student volunteers. They're sort of a self-selecting group because you have to apply, you have to apply, get recommendations from some teachers, and there's a selection process. So by the time they're there, they've already been quite selected, so to speak. So they're a very valuable resource for companies, and companies usually host special events just for students because they do want to talk to them and they do want to invite them over for internships or maybe a job later on. And it's a very, very good place to get a job, for instance. That's what I did. I was a student volunteer for, I guess, 2 years. Yeah, I think it was 2 years. And the last year, I wasn't even looking very hard. They had a wall where you could post your resume, and I left it there. And then I got emails, and one of them was from NVIDIA. And so then, went for an interview and got hired. I actually started, and you were asking about internships. I actually started as an intern back in 2007. So NVIDIA does hire a lot of interns. It's very good for both the intern and the company. I mean, it's very good for the intern because you get the chance to work at NVIDIA, which is generally a good experience. It's very good for the company because we get a chance to figure out if we want to hire you. That's mostly the point of internships, right? And there's an interview process and so on, but it is very much possible to get an internship at NVIDIA if you have some relevant work that you did during your degree or something like that. And really, if you have the will to do it, just apply. And it's not impossible. It's actually it's actually a lot easier than it sounds. And so I was talking about SIGGRAPH, going back to the student volunteer thing. It's a very good opportunity. I mean, not just for graphics, really for pretty much any area that might be related to computer graphics. It's such a big conference that everything is there. I mean, if you're a student volunteer, you always get a free conference pass. That's, I don't know, $1,000-something that you don't have to pay. You get some financial and housing support. Sometimes they will actually pay for your hotel room if you ask them to. Depends on the level of work that you're willing to do. So I think there used to be 2 tiers, one for just a few hours and another where you work most days. If you're on the if you're working most days, you're more likely to get housing. And also, they also pay for part of your trip sometimes if you apply and they agree to do that. They did pay for one of my trips and they did give me housing the first time. And if you were a student volunteer, there's also another program for ex-student volunteers where you get, instead of waiting doors, you actually get to be part of organizing one event. So I wound up being general chair of Graphics Hardware 2007 this way. And it worked really, really nice because most of the people organizing that happened to be at NVIDIA. And that's another great way to get to know people in the industry. So that's what I did. You can just go to that link and apply. Unfortunately, you're going to have to do that next year because the deadline was last week. That's not very convenient. And I guess that's it. Any more questions? Can we get a microphone?
The current platforms, desktop and especially mobile platforms, seem very. The current platforms, they seem to be held back more and more for because of closed source drivers. Is NVIDIA ever going to open source some of its work so that Android mods like Cyanogen mod can advance further, and also Linux desktop?
I wish.
Me too.
I can't comment on what the policy is going to be even 1 month from now, simply because I don't know, and even if I did knew, I'm not allowed to comment. Unfortunately, I don't see that happening. I mean, GPUs are a product that includes both hardware and software. NVIDIA traditionally makes a lot of effort on the software side. This is very visible on desktop GPUs, where I guess our drivers have less bugs for the most part, or at least we like to think so. And we also put a lot of effort in creating useful tools surrounding the drivers and the GPU itself, and development libraries like CUDA and other things that we have that we want to make. We want to make our product very useful, and that requires a lot of software effort. Because of that, we tend to guard our software quite closely, and I'm not going to agree or disagree with that policy. I also wish that people like the Cyanogen mod folks could get more access to our sources, because then my phone would work better. But I'm not sure that's going to happen.
Thank you.
I just have one question, only one. It's about NVIDIA Optimus. The new NVIDIA Optimus line of graphics card is proving to be a nightmare for most Linux users and FreeBSD users, at least. I mean, what's NVIDIA's issue with FreeBSD or Linux drivers for the Optimus?
I guess the issue is the target market for the Linux drivers are mostly workstations. Unfortunately, that sometimes means that NVIDIA may not implement certain features on Linux for, say, a mobile or a laptop chip. Having said that, we are interested in making that work, of course, and it may not be as high priority as it possibly could. But NVIDIA is always interested in making our products work very well everywhere. Unfortunately, sometimes we just can't do everything. And I think this is just one of those cases. We don't have a special problem with Linux or FreeBSD. We try to support those operating systems as well as we can, but sometimes some things have to stay behind. Anyone else? It's your last chance. Come on. Oh, feels like we're done. Okay. Thank you for coming.